Okay, now we're going to take a look at doing definite integrals. Before we did an indefinite integral, it would be something like this. When you do this kind of integral, you get the antiderivative. So your answer would be something like this. So again, that's called the indefinite integral. But when you have bounds, this integral starts from 0 and ends at 10. That's called a definite integral. And the way that I remember that is that you definitely know the answer. There's no plus c when you do a definite integral. This is going to actually equal a real number. It might be equal to 20, it might be equal to -2, but it's going to equal an actual number. Now, the way that you do a definite integral is it's almost the same as an indefinite integral. Our answer is just going to be 9x, but we're going to evaluate our answer from x equals 0 to x equals 10. And the way that you do that is you plug in the 10 first, and then you do minus, and then you plug in the beginning value of 0. So the answer to this definite integral is going to be 90. And I started with a real easy example. This is just y equals 9. It's a horizontal line. And we're doing the integral from 0 to 10. So it's kind of like the area under the curve. And I wanted to start with an example that you didn't need calculus to do. Everybody knows that the area of this rectangle is just going to be 90. Now, the rule that we just used to solve the definite integral is called the fundamental theorem of calculus. What it says is the integral from a to b of f prime of x is going to equal f of b minus f of a. So what's weird is we have an f prime of x here, and then we just have an f over here. So we're going to explain this example by figuring out what is f prime. So the 9 is supposed to be f prime of x. It's supposed to be the derivative of some function. We know that the derivative of 9x would give us a 9. So that means our function is just going to be 9x. So that's why a minute ago we said that our answer was 9x. We said we have to evaluate it from 0 to 10. And this rule is telling us that we have to plug in the 10 first, and then we put a minus, and then we plug in the beginning value last. So we plug in a 0 last. Now what's actually happening here is it's kind of like you're doing the inverse operation. You're doing the integral of a derivative, and those two things are kind of like canceling each other out. And that's why you're just left with an f. But because you're going from a to b, you have to take your f, you're going to evaluate it at b, then you do minus, and then you evaluate it at a. That's kind of what's happening there. Now what about the plus c? How come we're not putting plus c in here? Let's take a closer look at that. Well, it really wouldn't matter if you put the plus c. If we did put the plus c, I think a lot of you can see that this is the same. The derivative of 9x plus c would be 9. Those are the same. And now that we have the integral right next to the derivative, our answer is just going to be 9x plus c. But we want to evaluate it at the end first. So we're going to evaluate it at 10. Then we're going to put our minus. And then we're going to evaluate it at the beginning. So we're going to evaluate it at 0. Now look what happens when you put in your plus c. This piece is 90 plus c. And this piece, because the minus goes on both pieces, is going to be minus 0 minus c. So if you did put the plus c, it's the same constant. So the plus c and the minus c are just going to cancel each other out, no matter what value of c you choose. And you're just going to be left with 90. All right, for number 2, I'm going to start by doing the integral of this. That would be x to the 4 over 4. There was a 36 right next to it. So you can see that 36 divided by 4 is just going to give me a 9. So what I'm trying to do is I'm trying to take this function here and rewrite it as the derivative of f. And if I do that, then my final answer will just be f evaluated at the end, and then a minus, and then f evaluated at the beginning. Now let's check and make sure I did it right. If I do the derivative of 9x to the 4th, my answer is going to be 9 times. The 4 is going to come down, and the new power will be 3. So I'm getting 36x to the 3rd. So this derivative is equal to 36x to the 3rd. So that is good. So basically what I've done is I've rewritten 36x to the 3rd as the derivative of that red function. So f is that red function, 9x to the 4th. So if you match it up with the fundamental theorem of calculus, it looks like the f is my red function here. So my answer is going to be f evaluated at 3, and then minus, and then f evaluated at 1. And again, my function f is 9x to the fourth. So on the first one, I plug in a 3. And on the second one, I plug in a 1. Let's go ahead and simplify this. Your final answer is 720. Now, if you look at this picture here, basically what we've done is we found the area under the curve of y equals 36x to the third from x equals 1 all the way to x equals 3. So it's the blue shaded region right there. The exact area of that blue shaded region would be 720 square units. And in this example, we didn't say exactly what the units were. Now let's plug that in our calculator, see if we get the same answer. Now to do this integral on our calculator, I prefer starting with y equals, and we plug in our function. So I'm going to do that. Our function is 36x to the third. And I want you to notice I typed it in on y1. So now I'm going to go to the home screen. I'm going to do the integral. So that would be blue and 7. Make sure you put the right parentheses. We'll go back inside. We want to type in our function, but our function is in y1 of x. Then I'm going to put a comma and x, because the variable is x. And we want x this time to go from 1 to 3. So I'm going to put comma 1, comma 3. And then we'll push enter. And there we go. 720 was the final answer. Okay, for number 3, I'm going to start by doing the integral for 1 over x. We know that that's ln, and then the absolute value of x. We are evaluating it from x equals -5 to x equals -1. Our answer is going to be ln of the absolute value of x. We're going to start by evaluating it at the end. And then we're going to put a minus, and then we're going to evaluate it at the beginning. We can simplify this. Some of you already know that ln of 1 is just 0, so this piece will cancel out. And our final answer is -ln of 5. Let's check that on our graphing calculator. We're going to type in 1 over x on y1, and we'll go to the home screen. And we're going to do the integral of our function, comma x. Then we're going to put another comma because we're going to go from -5 to -1. When you type in the negative, do not use the minus. The negative is below the 3. If you mix those up, it will give you an error. Push enter. It's telling us that the answer is -ln of 5. That's the exact value. If you want to estimate, just push green and then enter, and it will give you an estimate, which is -1.609. Now, some of you probably wondered why, when I do the integral of 1 over x, am I getting ln of the absolute value of x? Why is there an absolute value? That's what some of you were wondering. Well, this problem is the exact reason why. This is the function y equals 1 over x. And again, the integral is kind of like the area, but we want to go from -5 all the way to -1. And if we don't have absolute value around that x, we're going to get ln of a negative number, which is not possible. So we would not be able to get an answer. So we have to have those absolute values there, or we're not even going to be able to do this kind of a problem. Some of you might also be wondering, why did we get a negative number for our answer? How can an area be negative? Well, we're going to learn more about the area later, but basically what's happening is these integrals are Riemann sums, and the height of every rectangle is negative. And so that's why we're getting a negative answer. It's because we're doing a Riemann sum, so we have a bunch of rectangles, but the height of every rectangle is the y value, and every y value in this example is going to be negative. So you have a positive width and a negative height, and that's why our area is coming out negative. We're not doing areas yet, though. We're just doing integrals. So when we start calculating areas, we'll talk more about how to figure out whether your integral is equal to an area or not. For now, we're just doing integrals, and a negative answer for your integral is totally acceptable. Okay, for this example, we're going to go ahead and rewrite this integral using the fundamental theorem of calculus. I'm only doing this to kind of explain what's happening here. Usually we don't do it this way, but I'm going to rewrite sine of x as the derivative of negative cosine. If you remember, the derivative of cosine is negative sine. So if I multiply both sides by -1, I'm getting that the derivative of negative cosine is equal to just positive sine of x. And that's important because I have sine of x, so I can write it as the derivative of negative cosine. And if we match it up to our rule, our function would be negative cosine of x. And since we're going from 0 to pi halves, I want to plug in the end first, so I want to plug in the pi halves first, and then put a minus, and then plug in 0 next. Again, my function is negative cosine of x, and then minus. Now, one of the most common mistakes is that people only put one minus here. Remember, the rule requires a minus, and the function itself is negative. So that's why I always recommend putting a box around it. And this way, you're less likely to make a mistake. It's negative cosine evaluated at pi halves, and then minus, and then again, negative cosine evaluated at 0. When I put these boxes around it, and then a minus in between, I'm less likely to make a silly mistake. So I'm less likely to forget this negative right here. So I always recommend putting those boxes around it. You evaluate it at the end. In this case, that's pi halves. Then you put a minus, and then you evaluate it at the beginning. In this case, that's 0. Now, minus a negative is going to be plus. Cosine of 0 is 1. You can bring down the negative, and cosine of pi halves is like cosine of 90, that's 0. So your final answer is going to be 0 plus 1, which is 1. Let's do that with our graphing calculator. I'm going to type in my function under y1, then go to the home screen. I want to do the integral of y1 of x, but I want x to go from 0 to pi halves. Push enter, and the answer is positive 1. Okay, again, we're going to rewrite this using the fundamental theorem of calculus. We want to write this as the derivative of some function. We know that the derivative of 3 to the x is going to be 3 to the x and then ln of 3. So we can divide both of these by ln of 3. That's just a constant. This piece will cancel, and now we basically have our answer sitting right here. So our 3 to the power of x can be rewritten as all of this stuff here. Then we can match it up to the fundamental theorem of calculus. So if you match everything up, our starting value is 0. Our ending value is 7. And we're doing the derivative of a function f. So our f is this function in purple, 3 to the x over ln of 3. According to the fundamental theorem of calculus, our integral is going to equal 3 to the x over ln of 3. We're going to evaluate it from x equals 0 to x equals 7. Remember, we got to plug in the ending value first, so 3 to the 7. Then we do minus, then we evaluate it at 0. Okay, I always recommend putting those boxes around it so you don't make any silly mistakes. We can simplify it a little bit. 3 to the 0 is just going to be a 1. And I would just leave your answer like that. Let's plug it in our calculator, see if we get the same answer. We're going to put 3 to the x in y1, and we'll go to the home screen. And we're going to do the integral of y1 of x, but we want x to go from 0 to 7. Push enter. Now this answer looks a little bit different, but we can simplify ours. We have an ln of 3 on the bottom, and the top is going to be 3 to the 7 minus 1. Let's find out what 3 to the 7 is. It's going to be 2187. So we are getting the same thing, 2186 over ln of 3. I'm going to rewrite this as the derivative of some function so that it matches up with the fundamental theorem of calculus. And the function is going to end up equaling this red piece here. Remember, we're doing the integral of a derivative. And basically what's happening is the integral and derivative are kind of like inverses. They kind of cancel each other out. So your answer is just going to be your f of x. But you do have to evaluate it from the start to the end. So we're going to have to evaluate it from x equals 1 to x equals 5. Now remember, you have to plug in the ending value first. So we're going to plug in a 5 first. And then we're going to put a minus. And then we have to evaluate it at 1. Again, I always recommend using boxes. And that's just so you don't make mistakes with this minus. Remember, this minus has to go on everything. Let's simplify it a little bit more. Looks like our final answer is just going to be 760. Plug it into a calculator, see if we got the same answer. We're going to type our function into y1, then we'll go to the home screen. We want to do the integral of our function, and our function is y1 of x. We're going to put comma x because we want our x to go from 1 to 5. Push enter, and we do get 760. All right, for this example, I'm going to take the 10 outside. Then we want to write this as the derivative of some function. And remember, these two things kind of cancel. So you're just going to be left with tangent inverse of x. But we do need to evaluate it from 0 to 1. Don't forget to bring down your constant. And again, when I evaluate this, I prefer to use boxes. We want to evaluate it at the end, which is a 1. Then we're going to put minus. Then we're going to evaluate it at the beginning, which is 0. Now, tangent inverse is a little tough for students to remember how to calculate. I want you to remember that tangent of pi fourths is equal to 1. So tangent inverse of 1 is going to give us pi over 4. So this can be replaced with pi over 4. And also tangent of 0 gives you 0. So tangent inverse of 0 is going to give you 0. So this piece can be replaced with the 0. If we simplify this, we're going to get 5 pi halves minus 0. So that's just 5 pi halves. Let's check that in the graphing calculator. We want to go to y1 and plug in our function, which is 10 over 1 plus x squared. Then we go to the home screen. We want to type in our integral. Our function is in y1 of x, but we want our x to go from 0 to 1. Push enter. And yes, we do get 5 pi halves. Okay, that's it. That was our last example. I do want to remind you how to type it in your graphing calculator. You're going to start with the integral, and it's going to give you the first parentheses. So you're going to have to type the last parentheses. Your function is the first argument that you type. Then you're going to type in an x, and then your starting bound, and then your ending bound. What I want you to notice is that there are 4 things, 1, 2, 3, and 4, and they're all separated by commas. So you're going to have 3 commas, 1, 2, 3 commas. And that's pretty much it. Remember, this is the TI-89 graphing calculator. And if you don't have a TI-89, you can use the free online simulator to practice with. The website for the TI-89 graphing calculator simulator is ti89-simulator.com.